Hello everyone, welcome to OPAL-RT learning journey, which today covers the topic of power hardware in the loop. We will talk about considerations and solutions for setting up closed loop test benches and introduce exemplary applications. First, let me introduce myself. My name is Sebastian Hubschneider, R&D engineer at OPAL-RT in Germany. I'll be responsible for hosting this webinar today and will present in the first half of our session. As a special guest, I'm very glad to welcome Professor Giovanni Decane from Karlsruhe Institute of Technology in Germany, who will introduce us to PHRL-related research in KIT's large-scale research infrastructure, Energy Lab 2.0. At the end of the webinar, we will answer questions from the audience, so please feel free to start sending your questions at any time. Okay. All is set. Let's start with a short view on the impact and relevance of hardware in the loop. What we see here on the y-axis is the number of publications that can be found in the IEEE Explorer containing the keyword hardware in the loop, drawn over the past 30 years. We can see that first papers were being published back in the 90s, where we barely had enough computational power. With a strong rise of interest, as obvious, in the year 2022, we had about 760 publications containing the keyword hardware in the loop, and obviously numbers still rising. Now, let's compare those numbers to those using the keyword power hardware in the loop, being depicted now in the lighter blue and on the right y-axis. Again, we can see a strong, or probably even stronger, rise of interest on the topic, finding 75 publications in the year 2022. I think this shows that PHRL actually by now is an established tool for testing, not only on the research state anymore. I think we can state that not only PHRL as a method itself is in focus anymore, but actually by now reaches an application level. Before going deeper into my presentation, let's have a short glance at the agenda. First, I want to recap PHRL as a method and talk about what it is, what is the optimum, and what is realistic. Next, I'll present what to consider setting up a test bench, and we will have an in-detail look on the crucial topic of interface algorithms. After a short summary on state-of-the-art PHRL, I then will give an overview on our solutions and on how OPAL-RT can help setting up your test bench. So, let's begin with PHRL. Well, what is a in-the-loop system? I think in general, we can state that in-the-loop systems are generic test environments for some type of component under test depicted on the right here. This component could be some kind of hardware or software device that is being interconnected via some interface with the test environment. This test environment actually is a replication of the natural environment of the component. Now, if our component under test is a real power device, which we want to run in its typical environment, we need a power hardware in the loop setup. Here, our interface doesn't exchange signals anymore, like digital or analog small voltage ones, but actually now the component, the device under test, is connected at its electrical clamps, so we have power flowing. So let's have a look at how it is working. Let's start the loop on the simulation side, for example, simulating a power grid. The voltage of one grid node is being sent to the FPGA and further via some communication interface to the power amplifier, which then amplifies the signal and provides it to the device under test. The device under test will react in some way, and here, exemplarily, the current is measured and fed back to the simulation environment, again via the signal chain. In order now to enable electrical interactions, step sizes of the simulation environment are required to be rather low. This is where the challenges arise, as we are talking of hundreds of nanoseconds to up to 50 microseconds, what would be a typical value for the simulation of power grids, for example. As we will see on the following slides, the efforts of setting up such a PHRL testbed are quite high, while having to think about stability and accuracy issues. However, it enables us of testing real hardware power devices. In the end, the realism of such a setup is quite dependent on the respective use case, we can say. So talking of use cases, what use cases are there? Well, we can distinguish between two different setup types. First, on the simulation side, we can simulate the behavior of power grids, for example, like be it a mains grid, be it an isolated grid, while on the hardware side, we will have loads, all kind of different loads, generators, power inverters, or even HVDC systems, for example. As mentioned earlier, here typical step sizes would be in the area of 20 to 50 microseconds. The other setup type could be actually having a real grid on the hardware side, depicted on here, while simulating machines, automotive components, or again, power inverters, HVDC lines on the simulation side. Here, well, basically due to the FPGA simulation, typical step sizes can go down to some microseconds or even hundreds of nanoseconds. Okay, now, after stating earlier that stability and realism can be challenging, why would we actually use PHL? Where are the benefits for us? Well, I think the benefits are in fact quite huge and overcome the efforts we have in setting up such a test bench by far, as it enables us for testing, validation, and evaluation of real power devices. So here we can test our devices in various environments. We can test it under extreme conditions. For example, simulate even system failures or partial system failures, which we obviously can't do in the real world. And on the other hand, it enables us for secure and reproducible testing. So in the end, we have a saving of time and cost in development of controllers, in development of power electronics, and so on. So now after this more like general part, let's have a closer look at PHL systems and also the challenges arising. Well, for the optimal PHL system requirements, what do we want to achieve? An optimal PHL system would cover all relevant system dynamics that are being present in the real system. Secondly, we require detailed models of all components that are relevant for the setup. And the third requirement is to have a quasi-continuous test environment, which we obviously need for interactions with a continuous environment. Here, this little word quasi actually, which represents the drawbacks of the software inherent discretization, is where the challenges of a PHL system arise. So yeah, let's have a look at the real continuous system we want to simulate with a PHL setup, just to see the problems basically where they arise. This real system consists of some voltage source, which could be the slack node in a power grid. We have some grid impedance and some device under test, which could be a heating resistor, for example. Now, comparing the left side of the real system with its digital representation, obviously we have a quite different setup. This includes the discrete simulation environment, some communication delays between different components, and the non-ideal behavior of the power amplifier and the transducers for measuring the behavior. This actually leads us to a conflict in realistic PHL setups. We want to achieve on the one side, we want to achieve high dynamics, which is reactions like step responses, for example, and also a high bandwidth in order to cover harmonic effects and oscillations. So for that, we will require a low simulation time step in order to be able to represent high frequencies. On the other hand, we want to have detailed grid models. Like here, for that, we need a high simulation step in order to have the computational power to simulate all this. And lastly, we want to have a stable system where the dead times in the system are actually a crucial topic. So again, we need to reduce discretization step size as good as possible. And here the loop finally closes. In order to stabilize the overall system, we need to damp it, which again limits our dynamics and bandwidth. So we can see for realistic test beds, we need to compromise between those three characteristics given on the right. This means for setting up a PHIL testbed in order to achieve a best possible solution for the specific use case, some basic considerations are to be made. As we need to compromise, first of all, we need to define our use cases and thus requirements in terms of dynamics and bandwidth. So here, basically, we need to consider, first of all, the scope of our PHIL experiments. So what kind of device and a test do we have? What is being simulated? Next, we need to consider the challenges, incidents, and the events of interest. What dynamics and bandwidth have to be covered in order to have realistic experiments. Third, we need to consider the given characteristics of the device under test, like how fast does the DOT behave, how fast is the higher level controller, and how fast do we need interactions with the grid. And last, we need to consider the required characteristics of the simulation environment. So what control behavior do we need to simulate, or do we want to simulate? How fast are those controllers, and what is the required level of detail here? So what does this mean? Well, in the end, we need some temporal classification of test cases, like given exemplarily here on the right side for power grids. For example, let's take one of the rather static test cases here. For under and over voltages, behavior of a device under test, depending on the grid, we don't necessarily have an influence on the grid voltage, so or it even can be neglected, and thus we don't require for closed loop testing here. However, for test cases where we actively influence the grid voltage, like phase balancing and reactive power control, closed loop testing is definitely required. One special area to mention here or to distinguish is actually the simulation of transient events being depicted here, where the CPUs are getting too slow and FPGA-based simulation is required. After defining the use cases, well, the second step or the next step would be deciding for a hardware interface. Here we need to consider, first of all, the type of communication between our real-time simulator and the power amplifier. So basically, it depends on the lab environment, on the physical distance of our real-time simulator and the power amplifier, which disturbances do we have around. Then we need to consider the amplifier bandwidth, dynamics, and signal quality. We need to consider the maximum time delay suitable for dynamic events in the communication. And last, the required transducer bandwidth and the maximum acceptable noise. So let's have a more detailed look at it, at the power amplifier at first. As mentioned, it has a crucial impact on the bandwidth and dynamics of our PHIL setups, especially as the typical transfer function, which we can see given here, is the transfer function of a second order low pass filter. And for the power amplifiers, thus the fundamental decision is required between a linear amplifier and a switching amplifier, as they are quite different. Especially the linear amplifier has its advantages on the technical side, like a high signal quality, high dynamics, a very high bandwidth, and where the switching amplifier has its advantages on the economical side. We can provide a full 4-quadrant operation. We have high feedback capability. We have a really high efficiency. And in the end, also it's the cheaper amplifier class if you want to reach very high power levels, or the only one with, you can realize those with. Next decisive point is the current and voltage transducers. Here, they typically have a sufficient bandwidth and dynamics, though this is not a problem. But a very crucial thing here is the noise and the error of those transducers. So basically the measurement quality. In the end, we will need a really high signal to noise ratio over the entire signal range in order to have exact simulations. And last, we need to care about the analog or digital communication between the FPGA and the power amplifier. So, and for the digital communication, again, whether it's an electrical or an optical communication interface. Okay, and now after setting or defining the test cases and deciding for a hardware interface. Our third big topic to consider would be implementing a suitable interface algorithm, which basically connects hardware and simulation environment in the end. So what to consider here? Well, as basically the topics talked about before, the required bandwidth and dynamics of the setup, the minimum calculation time for our environment simulation. We need to consider the utilized and amplifiers and transducers in form of their transfer functions, and also the impedances of the rest of the system, so the simulation environment and the device under test at all points of operation, as this really influences the stability in the end. And at some point, we need to compromise between the conflictive requirements as shown before. Where's the interface algorithm implemented? The implementation depends on the use case and how fast the interface has to be. We can implement it on the CPU of the real-time simulator. We can implement it on the FPGA of the real-time simulator, or even on the FPGA of the power amplifier, if the power amplifier is fit for this. And we could also obviously use multiple interface algorithms between the different systems. Now, typically implementing an interface algorithm, we need to further stabilize our overall system. For example, by using for the compensation of delays and dead times, or even by damping the closed loop application on software or hardware side. Here we could use passive components like, well, inductive components, for example, or use snubbers, or even use low pass filters, again, on hardware or software side. And well, obviously we are engineers. Would be too easy if it worked just like this. If necessary, at the fourth step, we would need to loop back to the first step and adjust everything. Okay, so much for the theory. Setting up a test bed in the end is it is very important to know stability limits and behavior. So if once we have our test bed, careful stability analysis is required. So let's do this exemplarily for the voltage type ideal transformer method. I chose this one as it's a straightforward interface algorithm, and I want to have a in detail look at it. So basically, let's take the schematic overview again. We had all the time. Now, how would this look in reality? We have our equivalent circuit here of some real system we want to emulate or simulate. We have some voltage source again. We have some impedance of the power grid, for example, and some load. So this real equivalent circuit now is being split up at the point of common coupling, and the interface algorithm is implemented in between the simulation part on the left-hand side and the hardware part on the right-hand side. So basically for the voltage type ideal transformer method, we would measure this voltage, apply it to the real system via the power amplifier, which is here represented by the ideal voltage source. And we will measure the current flowing in the real system and feed this back to the simulated system with an ideal current source in this case. So this basically, or like this, the loop is closed. And in the end, well, we have a closed control loop, which we can basically consider here. So let's have a look at this closed loop, at this control loop. It is depicted on the top right. Again, we have our source voltage. We have the voltage at the point of common coupling. Then we have some delay times for the communication. We have the transfer function of our power amplifier, supplying the voltage to the device under test, which can be represented by its impedance and some delay time again. And then we have our transfer function of the transducer and the time delays for feeding the signal back. Finally, on the simulation, we have our grid impedance and some additional time delay which corresponds to the discrete time step of our simulation environment. So for now, based on this control loop, for accessing the stability of the loop, typically, or one approach is to use the open loop transfer function. which for this case can be given as follows, or as seen here. The open loop transfer function basically is composed by the transfer function of the power amplifier of the transducer, and in this case by the software and hardware impedance, or by the ratio of those two impedances, and some delay time, which is the sum of the delays in the overall loop. And assuming those two as close to ideal, we can reduce our stability here, our stability condition, to the ratio between those two impedances, the simulated and the hardware one, and the delay time. Now, this obviously is only true for the given interface algorithm, the ideal transformer method. Besides this interface algorithm, there are many more interface algorithms that are proposed in literature, at which we will now have a short look. I want to give you a short overview on the most common of those interface algorithms, basically. No worries, the list only looks quite complicated. We will try to keep it on a very high level. What I want to point out is that for all interface algorithms, the open loop transfer function can be described as a function of the power amplifier, as a function of the transducer, the simulated real and damping impedances, as well as it's dependent on the closed loop dead time. So there are basically different damping impedances or something else is being utilized in order to stabilize the system in those interface algorithms. Well, this only to give a short overview. Now, enough of the equations. Let's assess those interface algorithms in a more descriptive way. What we can see on the following slides is a qualitative assessment of the characteristics of the different interface algorithms, which have different advantages and disadvantages. The most relevant characteristics of an interface algorithm, in my opinion, are the bandwidth and the dynamics, the stability of the overall setup, the scope, which here would basically mean the application range in terms of different test cases, and last but not least, the accuracy. So an optimal interface algorithm would obviously cover all 5 characteristics in an ideal manner. Now let's start with the ideal transformer method. We just talked about it. As just seen, it outputs the voltages or currents directly and feeds back the respective other. Its advantages are definitely on the accuracy, bandwidth, and dynamic side, while stability and scope are strongly dependent of the use case. So an upgrade for this ITM, for example, would be adding low-pass filters in the feedback path. We can see that the scope and stability definitely increase, but we limit our bandwidth, dynamics, and accuracy, obviously, by utilizing this filter. For the next interface algorithm, I want to introduce the partial circuit application. We use an existing impedance for damping by doubling this impedance on the software side. However, it's only applicable for systems where such a damp impedance exists in hardware. Otherwise, it would have a quite bad accuracy. The next interesting interface algorithm is the damping impedance method, which utilizes an impedance for damping on software side, which is an impedance that corresponds to the one of the device under test best possible. It's rather bad for changing dynamics, as impedance won't fit anymore at changing points of operation of the device under test. An upgrade of this damping impedance method would be the modified damping impedance method, where we upgrade it by adjusting the damping impedance utilized. The performance of the algorithm then is strongly dependent on the algorithm adjusting the guessed impedance, or the impedance of the device under test. Now, the transmission line model would use an electrically long conductor. It has very good stability characteristics, but rather bad accuracy if this conductor isn't there in the real world or doesn't exist. And last but not least, we have the time variant first order approximation, which is very good for linear loads. And yeah, well, as the name says, bases on a predictive first order approximation. So as we can see, there are lots of different basic interface algorithms and different modifications to those. However, there is no interface algorithm that could be considered as ideal without any drawbacks, what always somewhat will limit realistic PHRL testbeds. Here, the importance of computation power and thus reducing simulation step size gets quite obvious. We need to reduce the closed loop delay as far as possible in order to create a stable as possible setup without the need of an interface algorithm that damps our system too strong. Okay, so much for that. Enough of the theory on PHRL and interface algorithms for now. Let's summarize the last 25 minutes real quick. So far, I think we can state that PHRL is a mighty tool for development, testing, validation, and evaluation of power grids and its components. Although a careful system layout is mandatory and some compromises setting up a testbed must be made. We can say that an optimum for testbeds and respective use cases in the end must be engineered. Now, in the last couple of minutes of my talk, as pointed out earlier, I want to give a short overview on our solutions, on the solutions of OPAL-RT, and how we can help setting up your testbeds. Well, besides our core technology on hardware side, our different real-time simulators like the OP-4512 or the OP-5706, we can provide our customers with turnkey test benches and integrated power amplifier solutions. The first two test benches I want to introduce, though originally designed for HRL applications, are also to be used in PHRL settings, where power converters are tested in scaled down, well, real power environments and application. Let's start with the first one, with the OP-1200, our MMC test bench. This test bench is designed for rapid control prototyping of modular multi-level converters, for testing new topologies and switch configurations. It is a full operable standalone system. It includes at least an OP-4512 real-time simulator for simulation tasks, while also including up to 9 10-cell H-bridge submodules. The test bench can have a power rating of up to 20 kilowatts and operates at voltages of up to 700 volts. All this with up to 31 levels and a switching frequency of 50 kilohertz. Now, staying with the power converter test benches, for our second turnkey solution, we embed a test bench of our partner Empirics with our real-time simulator. The focus of this multi-purpose test bench is on the rapid control prototyping of power electronics, drives, and also smart grid applications. For this, Empirics PB half-bridge power converter modules are interfaced with OPAL-RT's real-time simulators, optionally also including the Empirics B-Box RCP. The test bench in the end can be set up for multiple voltage and current rating options, such as exemplarily 800 volts and 32 amps. It operates at a switching frequency of up to 50 kilohertz and provides the chances of a flexible system setup while maintaining a low-level hardware protection. Now, besides those power converter test benches, I also want to present the OPAL-RT power amplifier and microgrid test bench, as well as our solutions integrating third-party amplifiers. So again, let's start with the first one, the OP-1400, respectively OP-1420. It is a turnkey and high-fidelity PHRL test bench with an in-house built for quadrant switching amplifier of OPAL-RT, and it is an easy-to-use solution for microgrid applications, like emulating grids and DERs, and also integrating real hardware devices into this. Besides our own real-time simulator, it compromises up to 9 units of our PHRL amplifier, which allows for a great flexibility in application in the end. And optionally, we can also provide an OP-1460 microgrid busbar with it. The power amplifiers are operating as ± 400 volt DC, and we can deliver up to 30 kilowatt of power for 120 volt RMS systems, or up to 20 kilowatt for 240 volt RMS systems. Yeah, in the end, also our power amplifier provides voltage and current control modes. We have a full 4-quadrant operation bandwidth of DC to 10 kilohertz, and a dead time which we can provide below 8.3 microseconds. So I think we can state that our test bench is perfectly suited for PHIL applications, while also offering typical low-level protections like overload, short circuit, and temperature protections. So with this test bench, actually, we can also provide a validated microgrid model, also including controllers. This helps our customers, or can help our customers getting started in an established microgrid, which actually provides a generator, provides a battery energy storage system, PV plants, wind turbines, and a diesel generator, and also finally different loads. Obviously, because all main components of the system are being produced by OPAL-RT, this test bench can offer a high reliability and perfectly tuned interactions between the components. Now, lastly, besides our own power amplifier solution, we also integrate all kinds of third-party amplifiers with our real-time simulators, such as, but not exclusively, the ones shown on the right here. With those, different kind of microgrid and power electronic applications are feasible, but also motor emulation and traction inverter testing. Depending on the manufacturer of the power amplifiers, like on the partner we have there, we can offer analog, digital, or even fiber optic interfaces with all of our OPAL-RT real-time simulators. And via those connections, we can send set points and also for most amplifiers, receive measurement values gathered by the amplifiers to directly feed them back with as low as latency as possible. Our partners here cover switching as well as linear technologies, reaching up to hundreds of kilowatt and up to 30 kilohertz bandwidth, including one of those amplifiers as a part of a turnkey test bench obtained by OPAL-RT. We can not only help our customers selecting the best amplifier for their application, but also can supply them with full maintenance on the PHIL setup. In particular, this also includes the communication interfaces between the real-time simulator and the power amplifier, so you don't have to take care of this, or yeah, which can be a quite crucial topic, actually setting up those test benches. Well, with that being said, I want to conclude my talk. I'm proud to state that we as OPAL-RT Technologies can offer to be an integration partner for all kinds of PHIL setups. This starts at further developments for providing turnkey solutions, but also covers the research on interface algorithms and minimization of the necessary compromise using PHIL testbeds. For our customers, we can provide customer-specific support in optimizing PHIL applications. This starts at defining test benches, including CPU and FPGA models, as well as firmware customizations, and also covers long-term support on software and hardware solutions. During and after projects, we can, in the end, offer a strong partnership. And yeah, we would be happy to carry out joint research on all PHIL-related topics. Okay, yeah, that's it for now from my side. As mentioned in the beginning, in the end of today's webinar, we will have time for questions. So please feel free to write them in the chat already now. And now it is my great honor to welcome Professor Giovanni Decane from KIT once again, who will introduce us to his research environment. So, Giovanni, the stage is yours.
Thank you, Sebastian. I'm going to share 1 second my screen. Welcome everyone. Thank you again, Sebastian, for inviting me to this interesting webinar. I'm Giovanni De Carne. I'm tenure track professor at the Karlsruhe Institute of Technology. My background is actually on power electronics applied on power system, and during my early studies in my PhD, actually I began to work with power loop technologies because we wanted to test a new kind of energy technologies, new kind of power electronic solutions, and instead to prove it just in the lab with a simple environment, we wanted to have something more realistic. So I continue to work actually on this track, and currently I'm leading the Power in the Loop lab at the Energy Lab 2.0. What is it, the Power in the Loop lab? Actually is a large power in the loop facility. We have, as you can see from the figure, 1 megavolt ampere power in the loop testing hall. This is composed by 5 Exton 200 kilowatt Compiso that are actually connected with our OPAL-RT simulator. So we simulated the grid in OPAL-RT and we send the signal to the Exton amplifiers that can work both for voltage type, current type, and actually they are fully bidirectional. That is only one part of our testing capability. Actually, we have also smaller ones. We have a linear power amplifier of Spitzenberger, 45 kilowatt. And here the interesting thing is that we have actually a co-simulation environment between OPAL-RT and other simulators such as RTDS. And there we test usually smaller object, but requires a much higher bandwidth. What do we test actually? Well, we have different kind of energy technologies. We test actually, we have availability of 120 kilowatt flywheel energy storage system that is around 7.2 kilowatt hour of stored energy, around about 5 minutes energy at full power. We are testing currently a 500 kilowatt supercap system that is 1.6 kilowatt hour. And actually we can combine these two together so that we can create hybrid energy storage systems. But that's not all. Actually, with the smaller setup, we are working more on the gas turbine, so on the sector coupling problem, working as combined heat and power. This is relatively small, it's 3.5 kilowatts, so we work with our smaller power and the loop setups. And currently, we are developing a 50 kilowatt hydrogen power plant that is basically composed by electrolyzer, by a compressor, so a tank, and then fuel cells. The idea is that whenever you use any of these technologies, we don't investigate the technology from component point of view, but their interaction with the main system. And in particular, in this presentation, I'll make you a brief example of our performance that we have achieved with our flywheel in the way to control the frequency in the main grid. So Sebastian actually gave already a kind of introduction on why we are using power in the loop. The problem came from a really simple question. How can we validate experimentally new technologies? So I mentioned you flywheel, supercaps, we have batteries, hydrogen. What have we done up to now? Well, we used simulations. Do you have a lot of software able to do that? And you can do it in a really flexible way without much risk. However, many things cannot be really reproduced in simulations. And I give you some of these examples actually. The alternative is that I build my prototype, I put it in the field, and I see how does it behave. You have the highest accuracy, highest fidelity. However, it's time-consuming. Many times the field is not available, or you may cause some kind of disturbance to customer. So it's actually, you have really low flexibility in the testing. Well, the idea with the power and the loop is to combine actually the advantages of simulation, so working with a digital simulator such as OPAL-RT, and actually combining it with the real hardware that you are going to test in the lab. So basically you have flexible conditions and high fidelity as well. Let's make some practical example of what we are doing. You see here, this is our power and loop setup that we developed for our flywheel. So now we have here in green our 120 kilowatt flywheel that is a high-speed flywheel from the company Stornetic. This is a commercial device. There is nothing, let's say, built by us, if not the control boards for connecting the setup. This setup is actually connected to our power amplifier of the Eggstone family that he finds in our testing goal. Then what we do, we measure with an extension box of OPAL-RT, the 4510, the current of the flywheel, and we send this connection to our simulator. So in our simulator, what happens? We have a certain grid. This grid can be simple, can be more complex. It's up to us to decide. We decide where to install the flywheel, and we reproduce that point physically in our lab by means of the power amplifier. So you see here, now we have a loop, and in this loop, actually, we can have the flexibility of the simulation and the fidelity of the testing in the hardware. What can we do actually with that? Well, the first thing is to create a digital twin of our flywheel. So some model that is extremely accurate and is based on data. The problem is that when you work normally, you either work with the really simulation based on literature, or you work with reduced scale laboratory prototypes. What we try to do actually in our lab is to realize realistic test cases. For example, to create a digital twin of our flywheel using a real event, that is the UK frequency incident of August 2019. Do you remember when the UK had this large frequency drop to 48.8 Hz? Exactly that one we are doing it, and we are doing it with a full-scale validation. So we will use the full power of the flywheel. And then we will use the data to calculate the loss analysis. Why are so important the loss analysis? Because actually, when we model the flywheel is extremely complex. It has a lot of components. Some of them we can calculate the losses without too much problem. Like, for example, the speed-dependent losses, because we can use physics. The current-dependent losses, we can use the electrotechnic, the Kirchhoff law. However, there are other losses, like the constant losses, depending on the auxiliary power, that you need the real device to analyze this kind of losses. And they are strongly dependent by external factors, temperature, humidity, or also the time that you are using it. If you use for a long time, actually the vacuum pump and the AC, the conditioning system, requires much more power. So overall, actually, this can bring to some non-idealities that you cannot see in the simulation. Did we do a good job? Well, I believe so, because now you can see here on the right side, that is the grid frequency that has been reproduced with OPAL-RT, and the grid frequency that is actually measured by the flywheel and communicated by us with a Modbus communication. Below, you see what? You see the power that the flywheel injects when it reacts to the frequency change, both the power and the loop testing and our model. As you can see, the match between the two powers, the real one and the modeled one, is extremely accurate. It's really small, the mismatch. And you see that mostly in the state of charge, because if you have a mismatch in the power, for example, the auxiliaries are not taken into account, you will see it also in the state of charge. But here the max error is extremely small. Well, what can we do actually with the flywheel? We can offer control. In particular, we can offer frequency and inertia support to the grid, mostly if you consider that the future grid has really low inertia. In particular, what we did, we took actually our system and we developed an adaptive inertia emulation controller. This emulation controller was implemented still in Simulink, and better implemented in OPAL-RT, and we received some information from the Ethernet cable connected to the flywheel, okay, in this case, the state of charge of the flywheel, the speed, and we were sending out a communication signal from OPAL by means of an analog connection. The analog connection was really important because we could access to the PLC of the flywheel directly without needing to go through the Modbus communication that is usually much slower. Well, basically, what are the results? The results is that, of course, our proposed method worked better than we were expecting so much. But what was particularly useful for us was to implement also other controllers that exist already in literature. You see here controller in the paper 1, 2, and 3 that are actually our benchmark where we are fighting against. So we cannot just actually prove it against the classical Drup control that will be a too simplistic case, but actually we tested our algorithm in comparison with other algorithms, other strategies already existing in the literature. And you see, for example, here 3 of them. Well, in that case, we proved actually that our solution was much better in terms of frequency and rock-off control. And at the same time, we saw the counter effect on the state of charge with experimental results. So this is actually a really practical test case to demonstrate the need for a power and loop evaluation and why we cannot do this kind of analysis simply in a simulative environment. So I would like to close here my presentation. I would like to thank you for the attention, and I'm open for any question.